Okay, so now we're going to talk about water waves, and in particular, tsunami waves.
Yeah, so we've been using the rate equation a lot in this class. Is there a way to apply the rate equation to these types of waves?
Yeah, the rate equation comes up everywhere. And so one thing, before we start to look at the rate equation in particular, we need to look at some of the basic properties for these waves.
So basic properties like wavelength, amplitude?
Yeah, things like when we say wavelength, period of a wave. So let's draw a cartoon diagram of something like this. So if we have a beach here, and of course, we've all seen water waves at the beach here. And so if I draw some waves here.
Okay, so these might be like wind-driven waves?
Right. So these might be something like wind-driven waves. But if we went to the beach and say we had a camera with us and we took a snapshot in time, and we saw the waves out there, and we measured this distance here from peak to peak, that is called the wavelength. And, and traditionally, we label it with this Greek letter lambda.
Does it always have to be measured from peak to peak?
You could measure it from other areas too, like say you wanted to do trough to trough, but you have to be consistent when you're making those measurements. It's got to be from one point to the same point on the next wave.
Okay, so that's the wavelength.
Okay, so we have wavelength. And then also, the rate equation has time in it. So we need to think about things like time. This was just a snapshot in time.
Right.
But if we were out in the water, say, and we were on like a surfboard or some sort of flotation device, and the waves were coming in, and we were at a peak, and we started our stopwatch, and the waves kept coming, and we went down, and then we went back up again to the next peak, and we stopped our stopwatch, that would be the period.
Oh, okay.
So, and that's labeled with a capital T. So, and that is the period of the wave. Okay, so we have wavelength and we have period. What else do we need here? So we have a distance, we have a time. One more thing from the rate equation is the rate, right? So we know that the waves are traveling in this direction here towards the beach. So they're traveling with some velocity towards the beach. And so velocity is just the same that we always think about, just velocity here. Okay. So we have three basic properties of waves here. But we remember from the rate equation that we had something like distance, and this was very generic. Distance is equal to rate times time. Okay, so we've looked at these properties, and we have our equation, so we kind of need to associate these properties with these variables in the equation. So the distance, well, the one thing that we measured from the wave that was a distance was the wavelength.
Right.
So that becomes lambda here. And the rate is just the velocity. So that's v. And the time, we said, was the period. That's the time between successive peaks.
Right.
So we have wavelength equals velocity times period. So this is just a reformed rate equation, but for waves.
Okay. Okay, so we just went over some general characteristics of a wave, and here we're given an example of a tsunami wave, and we're told that the tsunami wavelength is 250 kilometers. So we could kind of think of that if we measured from, say, peak to peak. This distance is 250 kilometers, or I straight lambda.
Okay, so since we know that lambda is 250 kilometers, but we also are interested in the period of the wave, and that's denoted here by the stopwatches.
Okay, so we see that the first stopwatch, say time equals 0, and then we sit on our surfboard and we wait for this wave to travel. 30 seconds later, we would feel the next peak.
Right, so the wave is traveling in this direction, and at this time, at time 0, the peak is here, and 30 minutes later, that wave carrying that same peak is over here now.
Okay.
And so let's go ahead and write the rate equation out, but in terms of our wave properties here.
Okay.
So we know that the rate is equal to the distance over time.
Right.
Okay, so since we know that rate is equal to distance over time, we'll just plug in our wave variables here. So instead of rate, maybe we'll say velocity. And for our distance, we'll have lambda,
Or the wavelength.
or the wavelength. And then for the time, we need to know the period. Okay.
Okay, so from our example, we see that the wavelength is 250 kilometers. So we can just plug that into the numerator.
Okay. So let's do that. So we have 250 kilometers for the numerator. And what about the denominator?
So we saw that our time, or our period, was 30 minutes.
Okay, so we'll put that in here, 30 minutes. Okay.
Okay, and then we probably want to change this into from minutes into hours, so
Okay.
something like kilometers per hour. So we need to do a little bit of unit conversion here. We know there's 60 minutes in 1 hour.
Okay, so let's go ahead and multiply by 60 minutes over 1 hour.
Right, so now our minutes will cancel and we'll be left with kilometers per hour. So
Okay.
250 times 60 divided by 30 comes out to 500 kilometers per hour. So that's quite fast.
Yeah, so this tsunami is traveling about the same speed as a jet airliner flying across the Pacific Ocean.
Wow.